Hello, everybody. Hope you're enjoying your spring break. We're going to go ahead and get a little head start on Chapter 10 since we're going to be having a lot of folks gone in the coming week. So, really, this should make class time really easy by the time you get to school. So, I hope you're paying attention, taking notes, and should be a good time. So, as you can see, we are going to be looking into some circles now. We're moving away from all those quadrilaterals that we focused a lot on. Now we're going to look into a new type of shape, which are circles. And they have some nice little properties, and we're going to look at stuff that have to do with their tangents. So, anyway, I'm going to avoid getting on a tangent there. Ha. Okay. So, Mr. Keller likes to give the big three T's for this chapter, and those are terms, theorems, and test questions. So, each lesson is going to basically kind of have this sort of structure. So, we'll go ahead and just dive right in. And we're going to start out with our first T, which is terms. So make sure you're keeping good notes. Maybe make like a graphic organizer or something. This is stuff you're going to want to definitely study, be good at. Maybe make a Quizlet or something like that. First of all, we're going to start with, the most obvious term. That's going to be a circle. And that, looks like this. It's round. It doesn't have edges. It never stops. And essentially, in mathematical world, we define a circle as being the set of all points in a plane that are equidistant from a specific point. So that just means that the circle is the set of all of the points that are the same distance from a special point that we decide. So basically a circle is defined by a point and then a distance away from that point. So the specific point that we choose is called the center. And that's just, the point that all of the points of the circle revolve around. And that point is pretty important to know because we label a circle by its center. So here's a little notation thing like this image that looks like a circle with a dot in the middle, and then the letter here that denotes a circle with center P, or we just call it circle P. And so, again, since circles are defined by a point and some sort of distance, that distance is called the radius, and you can see it here in green. By definition, it's the segment whose endpoints are the center, so there's one endpoint, and then a point on the circle. So you have an infinite number of radii that you could draw within a circle, but each of those radii are going to have the same length. So any radius of a certain circle is going to be congruent to the same radius. So anyway, again, I'm getting a little off topic here, I guess, but key here is that the radius is the distance from that definition of a circle we just talked about. All right. Another term maybe you haven't been as familiar with, you've heard it before, it's called a chord, and there is some musical connotations to it, but here, mathematically, it is the segment with two endpoints where both of them are on the circle. So before, the radius had an endpoint at the center, not this time. Chords have to have endpoints, both endpoints on the circle. So an example, like I've been pointing at here, is segment BC. So if you want to go ahead and follow along in your notes. Technically, if we're looking at this picture and looking for another chord, you can see that BD also technically is also considered a chord. So I would say BD is also a chord. Segment BD. And so a more specific example of a chord would be a diameter. And a diameter is just a chord where the center of the circle lies on that segment. So diameters are pretty familiar terms to most of you, I'm sure. And in case you didn't also realize that, since a diameter has an endpoint on the circle and then also is the center in the middle, it makes sense that it's basically just going to be two radii put together. So make sure you're good and understanding of the fact that a diameter is equal to two radii put together. And so again, an example of a radius in this picture would be segment BD. So if you're following along, keep adding to this diagram here because we're going to be looking at some more terms. A secant line is going to be kind of like a chord, except chords were segments, whereas secants have to be lines. So a secant is just a line that goes through 2 points on the circle. So here an example would be the line DA. So again, notice the difference between lines and segments here. And so then while a secant has 2 points on the circle, a tangent line is a line that has only 1 point on the circle. And so an example from this picture here is going to be the line DE. So notice that the point E is not on the circle. I had to put it there so that way I could define my line. But the line DE has only one intersection point with that circle, and that's at point D. And the way I like to think about it is maybe like you have some sort of circular object and you're trying to place a board on top, like trying to balance a board on top of it. If it's a perfect circle, there's really going to be like one contact point between that board and whatever that circular thing is that you're trying to balance it on. So if you have trouble imagining that, maybe think of like a board sitting on a ball or something like that. And so if it's a perfect circle, it's only going to have 1 point of contact there. And that point is actually called the point of tangency, but we'll see more about that later. All right, so just to kind of make sure you're good with your vocab terms that I just threw at you, go ahead and pause the video and see if you can list all the examples you can see from this picture for each of these terms. So example, list all of the possible circles you see here, list all of the center points, list all of the possible radii that you see, etc., etc. All right, and so here are all the possible solutions. I tried, and if you wanted to, you could have even drawn in more based on the points that I gave you. So here are all the different examples. Notice that there's only one circle seen here, and there's only one center, whereas we have a lot of different radii and chords. There's only one diameter here based on what we know. But notice that radii, chords, and diameters are all segments, whereas secants and tangents, those are going to either be lines or technically you can also use rays. But know that these are always segments. These are always going to be like a line or a ray of some sort. All right, so going on to some more terms. We got one more for this video, and that's called a common tangent. So we know what a tangent is, and so a common tangent is going to basically be a line, a ray, or we'll even give you a segment for this one that is going to be tangent to two circles at the same time. So for example, a tangent line to these two circles would be like a board that can sit on top of one circle while also touching another circle. And so what I want you to do now is maybe pause the video again one more time and see if you can draw in and determine how many possible common tangents there are in each of these examples. So go ahead and pause the video. All right, so this is the solution you should have. And again, if you want to look in your book, this exact example is on page 653 if you want to take a look at what they have too. But I mean, it's basically exactly the same. I threw in this one though as a little bonus. So you can see here when two circles don't intersect, you're going to get 4 common tangents. So you can get 2 that sit on top, and then these internal common tangents as well. If the two circles intersect at 2 points, then you can't really get those internal ones, so you're just left with the 2 external ones. If the 2 circles touch each other at 1 point, then you get those 2 external ones, but then only one can be in the middle. And by the way, we call these kind of circles tangent circles, so kind of intuitive. But then if the 2 circles are lying within each other, maybe they're different sizes, and they're within each other and they don't touch each other at all, then it's impossible for them to have any tangents. And in this case, if 2 circles have the same center but different sizes, we call those concentric circles. We're going to see that term in the next video, though, so don't worry about it too much. All right, so that was our first T. Now we're going to look at our other big T, which is some theorems. So our first theorem is Theorem 10.1, and that is talking about some properties of tangents. So the first one here says that if you have a line that's tangent to a circle, then what's going to happen is it's going to be perpendicular to a radius of the circle, but that radius has to be touching the point of tangency. So, for example, if we have a circle and we know of a line like this line BR, if we know that it's tangent to a circle at point B, then we know that the radius going from the center to that point of tangency, we know that those two things are going to be perpendicular. So in this case, the line BR is going to be perpendicular to the segment BS. the next theorem for this section, and the last one as well, is going to say that if you have two tangents, like two tangent lines or rays or whatever, if you have two of them that touch the same circle, they're not necessarily the same line, but if they touch the same circle and then they intersect at a certain point that's not on the circle, then the segment from the point of tangency to that intersection point is going to be congruent. So, for example here, like if we know that we've got this line MA and another line AT that are tangent to S at maybe a couple different spots, then we know that the segment MA and the segment TA have to be the same. I like to think of this as like maybe the ice cream cone theorem, because it kind of looks like an ice cream cone, you know? So like if you have an ice cream cone, you got like your ball of ice cream right here, and then theoretically like your cone will come up and stop there. It wouldn't really make sense that your cone would have different sized edges here. Otherwise your ice cream cone would fall out and it'd be impossible to be there. So I don't know. I like to think of it as an ice cream cone theorem. If you like, I like ice cream though, so my mind always goes there. All right. So the third T of chapter 10 is called test questions. So this is kind of an example of some test questions you might see. So go ahead and pause the video. Based on what you've been taught so far, you should be able to figure out what the segment CD equates to. So if you want to pause it now. Alright, so this is what you should have. If you remember the first theorem we learned, then you can see that this tangent line DA is going to be perpendicular to BA, so drawing a little right angle. And then you can see, hey, we're getting a right triangle right here. Oh, shoot, I messed up. So, anyway, this should be a 7 because that's a big 7. Because these are two radii, and all radii are the same length. So what you do is you go ahead and find the length of this hypotenuse using your Pythagorean theorem, and so you get 12.2. But we don't want that whole thing, we just want CD. So what we'll do is we will subtract, not 10, but we'll subtract 7 from 12.2, and then we should get about 5.2 as our final answer for segment CD. All right, next one, another test question. We're given a couple of tangent lines to this circle Q. We know that the radius here is 5, and one of these tangent line, like this tangent segment, I guess, has length 12. And what I want you to do is I want you to find what's the measure of this angle PSR. So go ahead, pause the video. All right, here's your solution. So notice that I went and wrote in this 5 here as another radius, and then knowing our second theorem from this section, I can say that this segment up here is also 12. So using my Pythagorean theorem, I figured out, hey, this middle piece is going to be 13. Not that it really matters, but it's just easy to throw in there because that's a good Pythagorean triple. But anyway, so I also want you to notice, hey, maybe what kind of quadrilateral is forming here. It's one of the ones we learned about at the end of chapter 8. So regardless of if you notice that or not, by the way, it's a kite. So if we want to find PSR, I don't really know enough about this whole figure right here to just get this angle, but I can say that, hey, these triangles are congruent, so these two angles must be congruent, or if I know stuff about kites. So really, if I could figure out one of these angles from one of my right triangles, then I should be able to figure out the whole thing. So what I did was I saw, hey, I've got a tangent ratio here. I'll do tangent of PSQ, and that's going to be 5/12. So if I do my inverse tangent, then I'll find that this angle right here is about 22.6 degrees, and then times it by 2, and then I'll get my 45.2 degrees. So that should be your solution for that example. And that's all for the video. So that's section 10.1. So be ready for a homework quiz on Monday morning, and feel free to ask some questions, and then we'll make sure to get lots of practice in too with more practice problems and all that stuff. But again, be ready for a homework quiz. See you Monday.